Hi everyone, and this is a standalone short video on Gronwall's inequality, which is important in differential equations and in PDE. So the motivation for this is in estimating some norm or the size of a solution for a partial differential equation, we're led to some kind of inequality for the norm, and we want to deduce an inequality for the norm itself. Then Gronwall's inequality permits us to do this, and it says that the solution of a differential inequality is bounded above by the solution of the corresponding differential equality or equation. There are several forms of this. There's linear and nonlinear versions of this, but I'm going to state and prove the simplest version of the linear inequality, which ends up being useful in its own right. And it's quite simple, so I'm just going to try to do this with my 9% battery life. Theorem. Suppose that we have this function u, which is defined on this compact interval 0, t, where t is some real number, and that it's non-negative, and it's absolutely continuous, that satisfies this bound du dt is bounded above by some constant times u, and let's say that it has initial condition u naught for some constants, let's say c and u naught, assuming they're non-negative. Then, since the solution to this corresponding differential equation is known, it turns out that there's actually transfers, right? This inequality goes through. U of t is actually bounded above by the solution of the corresponding differential equation, which would be, of course, u naught times this exponential e to the ct. And this is, of course, for all t that makes sense, which is to say between 0 and big T, where u is originally defined. So let's prove this. We're going to let v of t denote e to the negative ct times u of t. And we want to bound this. We want to bound the first derivative. So dv dt, when we product rule this out, chain rule, is going to be, of course, e to the minus ct times, should be du dt minus c times u of t. And since we have the inequality that du dt is bounded above by c times u of t, this term is, and this is, of course, going to be non-negative, being an exponential. So then the product of these terms is going to be less than or equal to 0. Hence, v of t minus u naught is just the integral, let's say 0 to some fixed t, of dv ds. ds, which is less than or equal to 0, because we have the bound above, and u0 is non-negative itself, so we can just add it, and this doesn't change, which is to say e to the negative ct times u of t is less than or equal to 0, and this is, of course, true precisely when, just move this around. Oh, sorry, I think I wrote this wrong. This should be minus u naught, I forgot that term, less than or equal to 0, and this is true less than or equal to u naught. And this proves the result. This shows that if u naught is equal to 0, then u of t is identically 0, and this kind of bound, we're deducing this differential inequality means that the solution has to preserve the inequalities less than or equal to the solution to the differential equation that holds when you set the bound to equality. This turns out to be useful in PDE. So thanks for watching.